Hello everyone, welcome back to our series on transformer architectures and optimizations. So in this video, we're going to focus on three powerful techniques that actually have revolutionized how modern language models generate text. I'm talking about KV cache, incremental attention, and causal masking. Let me explain the benefit of each. So the KV cache actually is a technique that dramatically speeds up text generation by storing or caching the key and value representation of all previously processed tokens. So instead of recomputing these for every new token, the model simply reuses the cached values. So this reduces computation, slashes inference time, and make it possible to serve large models like GPT-4 and Llama to millions of users in real time. Where we will talk about incremental attention. The model only computes attention for the newly generated token at each step, using cached keys and values from all previous tokens. Importantly, like traditional transformers, where the query Q matrix is computed for every position in the sequence, making Q a matrix with a shape, sequence length, and embedding dimension, in the incremental attention, actually Q is computed only for the current token being generated. So it's just a single vector shape. It's one and the embedding dimension. So this means the computation for Q is one-dimensional, not spanning the whole sequence. So as a result, as the sequence grows, the amount of computation per token stays constant instead of growing quadratically. So this leads to much faster and more efficient text generation, especially for long sequences. And another technique that we are going to explore together is the causal masking. This technique actually ensures that during generation, each token can only see itself, and the tokens that came before it cannot see any future tokens. So this is crucial for autoregressive generation, where the model must generate text one token at a time in the correct order, so without cheating by looking ahead. So preserves the integrity and correctness of the generated sequence. By combining these techniques, modern language models achieve both high speed and high quality in text generation. So you will see how these optimizations work together to make interactive AI applications like ChatGPT that are actually fast, responsive, and natural. So by the end of this video, you'll understand not just how these techniques work, but why they are so important for the real-world AI system. So let's dive in. Before we dive deeper, make sure that you watched our previous course on the standard transformer and GPT architecture. I'm not going to explain all the workflow again, as you can see here. You will find the link in the video description, and we assume that you're already familiar with the multi-head transformer architecture and the roles of Q, K, and V matrices. As you can see here, the workflow you can find in the repository also. We start from the corpus, we create all the input and output sequences in batch size and transform from token to ID and to the embeddings, positional encodings. We arrive to the dense layers of the QKV. So at this point, there is our cache mechanism, okay? If you think about how transformers compute its output, you realize that each step, the model recomputes the Q, key, and V representation for every token in the sequence so far. As you can see here in the dot products between the query and key, we see that from the key, we recalculate all the matrix, all the values in the matrix for the seq length, okay? For example, if you consider the partial output like the cat set on, at the next step, we generate the word met, okay? So the key and value representation for the cat set on are exactly the same as they were in the previous step. Yet a vanilla transformer will still recompute them. We are literally wasting computation on things that never change. So that's where the KV cache comes in, by storing those K and V vectors after the first computation. So as you can see here, the transpose key, we are going to cache the previous keys, the previous step, and we just compute the new fresh key for the current token, okay? For example, for 1000 token sequence, this means we are performing 500,000 redundant calculations. So in production systems serving thousands of users, this inefficiency becomes a massive bottleneck. So your servers are burning through electricity and compute cycles doing the same work over and over again. So this is fundamental problem that KV cache solves. The KV cache actually is applied, okay, directly to the key matrices, but also later when we get the attention scores and we are going to multiply the attention weight for the value matrix, also the value matrix benefit of the caching. In this case, the shape of the matrix is batch size, sequence length, and projection dim. All the step before on the sequence of the sequence lengths that actually are the previous token values are cached, but the new fresh value is going to be computed for this current token. A representation of how the KV cache dictionary is structured, we will see later while studying the code, the Keras algorithm that help us to create this mechanism. The cache is organized in different levels. The first level is the layer. So this object represents layer 1, and next is going to be all the other layers. The second level is going to be key and value. So here we store the key matrix and the value matrix. And the next level is the batch level. So it's going to be batch 1, batch 0, 1, 2, and all the batches. The next level is the head. And at the end, we find directly the embeddings. So for each new iteration, we just add the new token and we append the new embedding of the new token at the end of the matrix, okay? And we just remove the last token from the previous iteration. And let's discuss about the procedure. Actually, the implementation involves two distinct phases, and understanding these two phase approach is crucial. The first phase is the prefill, and the second is the code. Let's explain the prefill step. The prefill phase happens exactly once at the beginning of our generation. This is when we process the initial prompt or context. So we process the whole query for all the sequence length, we process the whole key for all the sequence length, and we process the whole values for all the sequence length. Okay, this is in the first step. Now let me explain what's happening here in detail. So during prefill, we are processing the entire initial prompt all at once. We compute the query, key, and value matrices, as we saw, and for all our tokens simultaneously. So the crucial part is that we store the key and the value matrices in our cache for future use. So in the first step, we are going to cache. We cache this part, all the previous, okay, all the previous steps. Actually, in the first iteration in the prefill, we cache all the key and we cache all the values. The sequence length during prefill is the full length of our prompt. So if you have a 50 tokens prompt, the sequence length actually equal to 50 during this phase. We are doing this computation efficiently in parallel, of course, just like we would do during training. And actually, this is during training. So let's talk about the second phase, that is the code. Now actually comes really the clever part. So after prefill, we switch to the code mode, so where we generate tokens one at a time. But here's is where KV cache shines actually. Look carefully what we are passing to the model. So just imagine we are to the second iteration. We stored all our previous keys computations, and we're going to calculate just this new one. The new calculation is going to be batch 1 and projection dim. And we are only giving the model one new token at a time. So the sequence length is now 1, not the full accumulated length. Inside the model, here's what happens. So we compute the query matrix for just this one new token. But for the key and values matrices, we don't recompute them for the previous token. Instead, we take the new key and value for the current token and append them to our cached keys and values for previous steps. So now you might wonder why we are only computing query for the last token. We are not going to cache all the queries from the previous token, but we are going to we multiply only this new query for the matrix. Actually, we are going to execute the dot products between one dimension vector, okay, with a shape 1 actually, to the full matrices that also include the sequence length. So what it means that during prefill, the query matrix has this shape, sequence length, projection dim, okay, and batch size. But for the next computation, we just transform the sequence length and reduce to 1 because we are going to take only the last token. This is actually a crucial insight because in vanilla transformer during generation, we will indeed compute the query matrices for all the tokens in the sequence every single time. But here is the key realization. We only need the query for the position we are actually predicting, okay? So think about it, when we are generating token n, we only care about the attention scores and output for position n. The attention score for position 1 through n-1 we already computed in the previous steps. We don't need them again. We are not trying to repredict those tokens, they are already generated. So let's talk about causal masking. As you can see here in the workflow, we introduce this new step between the attention score calculation, the dot product between the matrices to get the score, and before the softmax application, okay? So now you might thinking, so if we're being so clever about caching, why don't we just use bidirectional attention like BERT? Wouldn't that be more maybe efficient? Actually, this brings us to one of the most important concepts in autoregressive text generation. And I want to explain not just what it is, but why it's absolutely essential. So causal masking ensures that when our model is predicting token n, it can only look at token 1 through n-1. So it cannot, under any circumstances, pick at future tokens. This might seem like an arbitrary restriction, but it's actually fundamental to how language generation works. Look at this step. This code actually creates what's called a lower triangular matrix. Let me explain what this looks like in practice. When we are generating token 2, the mask allows it to see 1 and 2. And so on, when we generate token 3, the mask allows it to see 1, 2, 3. Why this masking is so crucial? There are several fundamental reasons. For example, the first is the training inference consistency. So during training, your model learns to predict each token based only on the tokens that comes before it. If you suddenly allow it to see the future token during inference, you are asking it to operate in a completely different way than it was trained. So this will hurt the quality of generation significantly. The second, preventing information leakage. So imagine you are training your model to complete the sentence, the capital of France is. If the model could see that the next word after the blank is beautiful, as is the capital of France is Paris is a beautiful city, it will get an unfair hint about what the missing word might be. So this will make training less effective. And also the third is the real-world applicability. In actual applications, future tokens literally don't exist yet. So when ChatGPT is responding to your message, it doesn't know what it's going to say 3 sentences from now. So it has to generate text 1 token at a time. So just like human speaks, we don't know the end of our sentence when we start speaking. So now let me show you exactly how this masking is implemented. The clever trick is adding minus 1 in 9 negative 1 billion to the masked positions. We will see later in the code how it's applied, just to know that we are going to multiply for a really big negative number. We create the mask matrix. So we start with a lower triangular matrix of 1 and 0s, where 1 indicates position that should be masked, okay, future tokens, and 0 indicate position that are allowed past and current tokens. So apply the large negative value. So we take this mask and multiply it by minus 1 in 9. So masked position become minus in 9 and allowed position remain 0. And the attention score, before applying softmax, we add this mask to our attention scores. So if an attention score was originally, for example, 2.5 and it's a masked position, it becomes 2.5 plus minus E9, approximately minus E9, okay? And after we apply the softmax transformation, so it means that when we apply softmax for this course, the position with the really big negative number become essentially 0, since E superscript minus E9 is virtually 0, so while the unmasked position maintain their relative importance. So for example, if we have attention scores 2.0, 1.5, minus E9 for a 4-token sequence, where we are predicted the third token, so the softmax will produce something like 0.62, 0.38, for example, 0 and 0. Okay, so the model literally cannot attend the future tokens. So this masking is what makes autoregressive generation possible while still using the efficiency benefits of KV cache. It's time to walk you through the Python implementation of KV cache and causal masking. So in this video, I won't cover, as I already said before, the full GPT or transformer architecture. So if you need that background, please refer to the video linked below. So instead, I'll give you a high-level overview of the main classes and function details you can explore in the other video, and we'll dive deep into the code blocks that implement the KV cache and causal masking to understand exactly how they work. At the end of this section, we are going to test and compare both the vanilla transformers and the new empowered KV cache and causal masking transformers. So let's start with a fast overview of the main parts. So we have the multi-head attention. So this multi-head attention actually is the layer that implements the core self-attention mechanism with support for multiple parallel attention heads. So it split them across the num heads and computes scale.product attention. Optionally, like in this case, applying a causal mask for autoregressive decoding. So when we use cache true, okay, the parameter use cache true, it incrementally updates and reuses the key value cache to avoid the recomputing past attention during generation. So finally, it concatenates the Perez outputs and projects them back to the original embedding dimensions. We have also transformer block here. The transformer block composes a multi-head self-attention sublayer followed by position-wise feed-forward network. So each wrapped with the residual connection and layer normalization. So it applies dropout after both the attention and the feed-forward sublayers and the regularization. So during generation, it passes along and updates a per-layer KV cache to speed up autoregressive decoding. So the output is normalized some of the block's input and transformed feature. But I repeat, for further details, please refer to the previous video and get the link you can find in the link below. We have the transformer model, so it builds actually a full transformer stack for sequence modeling, including token embedding, sinusoidal positional encodings, multiple transformers block layers, and final layer projection to vocabulary logics. It supports both training, prefill, and incremental decoding by slicing the positional encoding according to start pos and treating a list of KV caches through the layers. So during generation, with caching, it returns both the logics and update caches for each layer. So at inference, you can pass in a single token sequentially, leveraging cached key and values to produce new outputs. We have also the create sequences function. It create actually converts a long integer encoded text sequence into overlapping input and target example for next token prediction. We have generate text with KV cache, and is important for our tutorial. This function performs autoregressive text generation using the transformer with optional KV cache optimization. It first vectorizes and pads or truncates the start string to sequence length, runs a prefill pass to build the initial cache, then it iteratively generates num generate token one at a time. So each time passing only the newly predicted token into the model along with the updated cache. The sampling actually is controlled by a temperature parameter applied to the logic before drawing to a categorical distribution. If use KV cache is false, it falls back to naively refeeding the entire sequence each step. So we have generate text, that actually is a thin wrapper around the generate text with the KV cache. We have load corpus that actually abstract away the details of loading a training text either from a remote URL, like a web source or local file. We have the train, and actually the train function orchestrates end-to-end model training, okay, loading the corpus, vectorizing the text, creating training sequences, building and compiling the transformer model. All these block is really well explained with a previous video. We also have the generate, actually the generate function here. So this routine actually loads a previously trained model and vectorizer from disk, generate the sample text with or without KV caching. So we are going to use both of them and compare them. So let's start with the heart of our implementation, so the attention mechanism with causal masking. I want to show you exactly what happened when we compute attention line by line. Let's go to the attention part. So as you can see here, we have score. We're applying a matmul, actually is a dot product. So what's happening in this first line? we are computing the dot products between our query and key matrices. So notice that transposed B is true. This means that we are transposing the key matrix as we saw before in the workflow. So we are actually computing Q times key transpose. Okay. This gives us similarity score between every query position and every key position. So think of it in this way. The query is asking what am I looking for, and the key is answering what I contain. So the dot product tell us how similar they are. Our query has shaped batch size by number of heads, by current sequence length, by projection dimension. So the key has batch size by heads, by total sequence length, by projection dimension. After the matrix multiplication, we get a result with a shape batch by heads, by current sequence length, and by total sequence. This is our attention score matrix. So if we go to the next line, the dim-k, actually this get the projection dimension, so that is the last axis of the key, and the scaled score divided by square dk. So actually this normalizes the score. So scaling by square root of the dimensions keeps our gradients stable during training and prevents the saturation problem. So this is the important part. We are applying a causal mask for autoregressive generation. Actually, it's here where the causal mask comes into play. This is absolutely critical as for our regressive generation. So we add negative 1 times 10 the 9th power to position when we want to mask. We saw in the workflow before. So why such a large negative number? Already explained, because after we apply softmax in the next step, this large negative value becomes approximately 0. So this is how we prevent token, for example, I, from attending to token J, where J is greater than 1. In other words, we prevent the model from cheating by looking at future tokens. So the next line, we have weights and output. So this converts scores to probabilities. We are applying the softmax. And here we have the weighted sum of values using attention weight. We are going to perform a dot multiplication between the weights and the value matrix. Let's see the game changer, actually, the KV cache implementation. So let's dive into the KV cache, how it stores, how it creates this dictionary that we saw before. This is what makes everything fast. Let me show you the multi-head attention call method where the real optimization happens. So we are going to use this function, and we have the batch size and seq length. We get the number of sequences in the batch here. We get the length of the current input sequence here. We start by setting our dimension, and then we are going to compute, okay, query, key, and value for the current input tokens. So the cache optimization doesn't change this step. We still need to compute these matrices for whatever tokens we are currently processing. And this step, we are going to split our embedding dimensions across multiple attention heads. So this allows each head to focus on different types of relationship and enables parallel processing. This is where we create our dictionary for the cache. So we check if we should use cache values here. Okay. It retrieves the previous computed keys. It retrieves the previous computed values. Ensure the cache actually is valid, combine the old keys with the new case with a concatenation, and also here recombine old values with new values. At the output of the function, we get the new cache, the new updated cache. So let's talk about the causal masking. As you can see here, we get the sequence length cached plus new. Okay, we create a lower triangular mask here, and we invert 1 for max and 0 for allowed. But during actually KV cache generation, when sequence length is 1 and total sequence length is 4, for example, our mask becomes just one row. 1, 1, 1, 1. This means that new token can see all the previous token. We are only computing attention for the new token, but it should attend to all the previous token. Let's see how we manage caches across multiple transformer layers. We can now go to positional encoding with cache is critical. So the start position parameter tells us where the new token belongs in the sequence. So this is essential for maintaining positional awareness during generation. So during the code phase, we only encode the position for the new token. During pre-fill phase, we encode all the position. As you can see here, check if we need to initialize cache, and if yes, we create an empty cache list for each layer. And our cache architecture, actually, we have an array with one entry for the transformer layer, and each layer gets its own independent cache containing key and value tensors. So what we are going here is we have a list to store updated caches. We iterate through each layer here. We get the cache for this specific layer. We process through layer with cache, and we store updated cache for this layer in this part. It means that we process through each transformer layer sequentially. Each layer gets its own cache slice and updates its own cache independently. So the cache grows consistently across all layers, maintaining the same sequence length at each level. So let's talk about the two-phase generation, how we implement in the code. So now let's examine the complete two-phase generation process in our generate text with KV cache function. This function actually, as I said before, demonstrates how we achieve incredible speedups in practice. Here is the function. So during the pre-fill phase, we process the entire prompt at once, as we said before. If it's use actually KV cache, we are going to process the entire prompt, okay, and start from position 0 in this part. During pre-fill, we process the entire prompt with shape 1 by sentence length. We compute query key and value for all prompt tokens simultaneously. We fill our cache with the key and the value matrices for all layers. So we get the prediction for all position, but we only use the last one for generation. Let's see where is the decode phase. And actually the decode phase is here, in this part. For it loop each token to generate. The next token, actually here, convert the token indeed to tensor, 1, 1. And the prediction at KV cache, actually it process single token with cache, enable cache usage, set current position, and inference mode. Okay, training false at inference mode. So during the code, we process only one new token with shape 1 by 1. We compute query, key, and value for just this token. So we concatenate with cached keys and value matrices. So we update the cache with new tokens, key, and value. We get a prediction for this position only. Before launching the script, let me explain you how the main function and the generate compare function works, okay, in detail. Let's start with the main. Actually, this is our program's entry point, the control center. So as you can see here, we have different options, okay. Train, if we put the value train, actually only trains. Generate text. Generate compare we are using for our experiment. It compare KV cache versus standard generation, and both does training followed by comparison. We also have a use KV cache, that actually is a parameter only for the generate mode. We have the weights path. It's the file path where train model weights are saved. The vectorizer path is also a file path where the text vectorizer and model parameters are saved. If the model train is, as you can see here, we print a header and we call the train function. This will train a new model from scratch actually. If the model is generate, we call the just generate function with our configuration parameters. This load pre-trained model and generate text. We have actually generate compare. If the model generate compare, we call that function to benchmark KV cache performance against standard generation. And at the end, we have both. It first train a model and then run the performance comparison. Let's see together the train function here. Let's find the train function. Here we go. Let's dive into the details. We have actually the corpus source. It can be local, okay, to get a TXT file. That is this one. We're going to use a really small corpus. We're not going to train the model, of course, from scratch for real. It's just for didactic purpose, just to compare the performance of the KV cache. So after that, we load the corpus here. Actually, we limit in the vocab size, we limit our vocabulary to 10,000. We also set the sequence, okay, each training sentence will be, in this case, 100 tokens long. We create a text vectorization layer and converts text to integers. We adapt the vectorizer to our text corpus to build the vocabulary, okay? So the next lines actually here, we create the sequence. So it generates an overlapping sequence with the sec length. We add assertion to ensure our data is valid, and we convert to TensorFlow tensors for training. Then next, we have this variable here. So actually, embed dim is 256, is the embedding dimension feature that represents each token. We have the number of attentions, heads. FFDIM is actually the feed for network dimensions. Of course, these details are well explained in the previous video, as I said before, but we are going to repeat again just to understand how is trained the model. In this case, the number of layers of actually our transformer, the number of transformers blocks in this case. And we go to the next step, that is we save all the visual Keras. We use visual Keras to create a visual representation for our model architecture, so you will find it in a specific folder. We have various parameters controlled through appearance and visualization. I'm not going to spend time for this. We have also the tensor board set up if you want to get more important insights. And here we go. So here we set the early stopping to prevent overfitting. We train for, in this case, just 20 epochs. That is just really small. And with each batch size with 32, okay? And we save the model weights and in HDF format. We save also the vectorizer. We save the vectorizer here with this path. Yeah, this actually allows to reconstruct the exact model architecture later. We plot something, we save some with total training loss over epochs. We save the plot to the log directory. We return also the train model and parameters for further use in this case. Okay, so let's see the generate compare function. The most interesting function actually compare KV cache and vanilla approach. In this part, we load all the saved parameters. So we load the pixel vectorizer, then the model parameters. We extract all the necessary parameters and reconstruct the model. And we have the comprehensive error handling if something for missing files or parameters. We go there to this part. Actually, we create a new model instance here. Okay. We build the model by running a dummy forward pass, and we load the trained weights with error handling. We load the weights here. Here we get into the comparison part. So actually we create the timestamped output directory here. We define the test parameters like star string, token counts, and temperature. Okay. And we initialize the result list to store performance data. The star string is the object for hour, so we just want to start from a little substring of our corpus. But of course, the sentences are going to be really chaotic because it's not a long training, it's just a really fast training. Actually, we have a nested loops because we want to test different temperature and count combination. We want to see different parameters with temperature and token count to see how the KV cache behave comparing to the standard approach. So actually in this part, it record the start time, it called generate text with a KV cache, with the use KV cache true. It measure the elapsed time and print timing information. And here we have the test without a cache. So we are going to, actually it's the same process as before, but with the use KV cache false here. And this forces the model to recompute attention for every token. So here it calculates the metrics that's going to be saved in our output file. So the speed up actually is how many times is faster KV cache is actually. Time saved, okay, this is the absolute time difference. The percentage saved is the percentage of time saved. And we store all the result in a dictionary for later analysis. Actually, we have the comprehensive printing of the result analysis. It creates actually a formatted table showing all the results here. And we calculate also the averages here. And next is saved all the result to a detailed text file for later analysis here. Okay, it's going to be the same as we print, going to be saved in the file. At the end, it actually provides an intelligent insight based on performance results. let's try the script. So first of all, we activate our virtual environment in Python. We set our script in the train mode because we want to train the model first. And here we go. We're going to Python main.py. So we see the architecture of our script, of our model, and we're going to wait the training for all the epochs. The training is completed. As you can see here, we save our model weights in this file, and we also save the text vectorizer here. So we are ready actually to launch our text generation, specific our comparison. I'm going to change the mode in generate compare here. And here we go. We launch the script again. Okay, as you can see here is starting to test. The first combination is temperature 0.7 with 50 tokens, 100 tokens, and 200 tokens. As you can see, as the number of tokens grows, the time saved also grows. We're waiting for the process to finish. So after this, we are going to analyze the final output. So here we go. This is our report. So KV cache versus standard generation performance comparison. So let's dive into the impressive KV caching results. So our key findings show that an average speed up of 1.74 across all the tests with 42.5 time savings, nearly half the generation time eliminated. So the total processing time dropped from 64.9 seconds to just 36.9, achieving an overall 1.76 per speed up. It's interesting, for example, that temperature 1.0 consistently showed a slightly better performance than temperature 0.7, particularly achieving 1.84 speed up for 50 tokens and 200 tokens generations. This likely stems from how temperature affects attention patterns. True differences are modest, showing KV caching is robust across generation strategies. Whether building chatbots, content generation systems, or large-scale NLP application, KV caching represents a significant step forwards in making language models faster and more practical to real-world use. So thank you for watching. Subscribe for more ML optimization content.